Hey folks, I'm back to talk about kind of the next layer of Lewis structure where we've got some extensions, some new opportunities for different types of covalent molecules, and some exceptions to the rules. The first of the kind of next level Lewis structure abilities I need you to have is I need you to be able to draw a Lewis structure for a covalent compound that has an overall charge on it. These are your polyatomic ions, guys, and they're actually all around us and they're really important. So I want you to be able to draw a Lewis structure. But the nice thing is it's actually not that hard. All you're going to change when you do your NAB is that when you get to the available count, if you have a negative charge, you're going to add electrons because that means you've added extra electrons than would be found in the neutral atoms. If you have a positive charge, you're going to remove electrons. Let me show you how this works with the polyatomic ion ammonium, NH4 plus 1. Okay, let's nab it. So, needed, nitrogen needs 8. There are 4 hydrogens, they each need 2. So that's a grand total of 16. Available, first part of this works the same as you guys have been doing. So nitrogen has 5 available and each of those hydrogens have 1. This has a positive charge, which means it has lost 1 electron compared to the number it would normally have in a neutral molecule. So you're going to subtract 1 electron from that. This gives me a total of 8 available electrons. For bonds, I am going to take 16 minus 8 divided by 2. That's 4 bonds. So when I take my nitrogen, since it's different, it goes in the middle. I put my hydrogens around it. I connect each of those to the nitrogen with a bond, use my 4 bonds. I've actually used my 8 electrons, 2, 4, 6, 8. Double check valence. Each hydrogen needed 2, check. Nitrogen needed 8, check. So your Lewis structure is almost done. The only other change that we're going to make now that we have a charged species is we are going to put square brackets around the Lewis structure and show what the charge is on the outside, because that positive charge is shared amongst all of those atoms. Let's do one example with a negative charge. So let's take the polyatomic ion hydroxide. Here again, nabbing it. Needed 8 for the oxygen, 2 for the hydrogen, that would be 10 electrons. Available, oxygen has 6, hydrogen has 1, it has a minus 1 charge. So I am going to add an extra electron. That makes 8 electrons going on there. And then when I look at my bonds, that means I need 1 bond. Oxygen to hydrogen, there's that 1 bond. Filling in the valence, hydrogen has its 2 from the bond. 3, 4, 5, 6, 7, 8 electrons now around oxygen, and I've used a total of 8 electrons, so my Lewis structure is good. All I need to do is put my square brackets around the outside. If the charge had been minus 2, I would have added 2 electrons to it. If the charge had been plus 3, I would have subtracted 3 electrons. So if it's positive, you're subtracting electrons to whatever that charge number is. If it's negative, that's how many electrons you're adding to your available count. Okay, that's exception or extension number 1. Let's talk about resonance structures as our second extension. In a molecule that has resonance structures or resonance forms, there is more than one equivalent way to draw the molecule. Well, what do I mean by that? Let me show you with the polyatomic ion carbonate. We're going to nab it, making note to add those extra 2 electrons from the minus 2 charge. And I have 4 bonds. So when I go to draw this, I put my carbon in the middle. I put my 3 oxygens around it. Where do I put the 4th bond? They're all the same. It doesn't matter. I could put it here, or I could put the double bond to the oxygen that I've drawn at the bottom, or I could put the double bond to the oxygen on the right. This is what I mean by the fact that we have more than one equivalent Lewis structure. We got to go through and add our lone pairs because we wouldn't be done without that. And each of these, of course, has a charge on it, so it has a minus 2 charge. So which one's right? Well, it turns out that the actual molecule is a blend of all three of these. So what I mean by that is I actually don't have one oxygen that has a double bond, which would have a shorter bond length, and two that have single bonds with a longer bond length. Instead, all of the atoms really have about a 1 1/3 bond length. So they're like in between being single bonds and double bonds, but they're all equivalent to one another. It turns out that resonance is actually incredibly important because not only does it change the bond lengths and bond strengths within a molecule, but having more regions for the electron density to be found in, that's another thing that's stabilizing. It reduces electron-electron repulsions, making molecules that have multiple resonance forms unusually stable. And that changes the chemistry. We find these around all over the place. And so it's totally worth being on the lookout for resonance forms. The last set of exceptions we're going to talk about here are exceptions to the octet rule. These are atoms that when they're in a covalent compound don't need 8 electrons. Either they can have and accommodate extra electrons beyond the typical 8 electrons needed to fill a valence shell. Those are called our hypervalent atoms. Or they can have fewer. And we call those atoms that are satisfied with an incomplete octet. So let's take a look at these. The atoms that tend to have incomplete octets are aluminum and boron, which are happy with needing 6 electrons, and beryllium, honestly, which is cool with 4 electrons. So how does this impact you when you go to draw a Lewis structure? It means that you're going to change your number of electrons in the needed count in that first piece. So if I take a look at aluminum trichloride, AlCl3, when I go to write my needed for my NAB, I'm going to put 6 as the number that aluminum needs. And then everything else from here on out stays the same. This is 30. And then when you go to draw your Lewis structure, you are only going to put 6 electrons around the aluminum. And it's stable at that point in time. So that's an incomplete octet. Expanded octets you see often and really only with heavier, larger atoms that are in the 3rd row and below. There's a lot of debate as to exactly how these work, but the general gist of it is that your atoms have to have d orbitals that can somehow get involved in the bonding. Again, there's some actual logistical current debate over exactly how these bonds work, but they're kind of cool. So the only thing you do is you're going to nab it just like you normally would, but you're going to know you're going to have an expanded octet. You're going to alert because the number of bonds that you are going to calculate is going to be less than the number of atoms you have to actually attach. So if I take a look at something like xenon tetrafluoride and I go to nab it, when I get to the bonds part, I'm going to find that I only need 2 bonds, but I have 4 things to attach. That's your flag to know that you have an expanded octet. You will still draw a bond, a shared pair of electrons between the central atom and every atom that is binding and being covalently bound to this molecule. And then you're going to be smart and you're going to count your electrons. I have 36 available electrons. I have to use 36. I have already used 8. You will start filling valence for your outer atoms just like we always do. I've used 8 so far, 9, 10, 11, 12, 13, 14. That fluorine's happy. 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Any extra electrons you have go on the central atom. 33, 34, 35, 36. So you will notice that xenon, if you count how many electrons it has around it, has 2, 4, 6, 8, 10, 12 electrons around the xenon. This is something that makes it what we call hypervalent, or has an expanded octet. It has more than just the standard 8 valence electrons around that central atom. It does happen. Don't freak out. Just know when you get to that bond tab for your nabbing, you're like, ooh, something's weird, that you're likely to have an expanded octet.